Okay, let's get started. Hello and welcome everyone to Ethproof call number 9. The topic of today's call is formal verification. This is a long overdue call and is going to be led for the most part by Alex Hicks, who will be taking over very, very soon. But I do have a few slides that I'm going to share super quickly. Just going to mute a few people up to prevent the echo. So one is that I'm very excited about formal verification since a few weeks, not only for security, but also for performance. We have projects like EVM ASM, where once we have the end-to-end formal verification, we can really start grinding on performance. We have something like the proximity gaps results, where we have an initial result, we have conjectures, and we can incrementally work towards better performance. And just generally speaking, it seems like auto research is taking over the world, and formal verification is a match made in heaven. If you are new to the Ethproof calls, there is a Telegram group. This is the link, ethproofs_community. And there's also a QR code just to make it slightly easier for you to join. There's about 600 people there, and we try to keep it relatively high signal in that group. So this is the historical calendar of Ethproof calls. We've had 11 of them, like 2 B calls, and the next call will be on August 15th, dedicated to binary fields. So if you've been on Twitter recently, there's this new proof system called Flock, which is based on binary fields. It's really, really exciting because it has similar performance when proving hashes relative to prime fields that use ZK-friendly hashes like Poseidon. So it would be potentially a way to use a traditional hash function like Blake or SHA-2 or SHA-3 and have higher security overall. So that's going to be the topic of the next call. And yeah, I just want to hand it over to Alex Hicks.
Yeah, thank you. I think we'll get straight into the talks because we have many of them and because these calls always run. But yeah, we'll basically cover a couple different topics. Most of these are received ZKVM related, and people will be aware of the kind of verified ZKVM effort. So this will cover ZKVM circuits and verification, cryptography, compilers, the EVM, and work on verifying EVM. But then we'll have a bit at the end as well about smart contracts, since there's been some exciting work there. And I think we can basically try to start the talks as soon as possible. So Shuki, if you're ready, the floor is yours.
Sure. Let me share my screen. Oops. Okay. Hi everyone, here's Shoki from Nix Foundation. So today I'm talking about our formally verified ring consensus clients. So our goal is implement drift between specification and implementations. We're using the ring as a backend, which formally verifies consensus logic. This design inspired by Cardano. They have a Haskell client, which backend is implemented in Agder. So here is a sketchy architecture. We proved the kind of state transition and the fork choices. And here is the consensus logic. You may know it's so important part. And as you may know, we can run the compiler in Lean, which introduce C program. So we can binding with any other C ABI languages like Rust or Go. So we're using the Rust as a runtime, which has a bunch of side effects like networking or storages as well. So here is a state transition benchmark. We can benchmark the assuming 4096 validator defined in Lean spec. As you can see, the results are lower than SOL in Lean spec. Sorry, I guess this 200 millisec is not correct. It's, I guess, 800. Anyway, so we determined that this is suitable for practice use. However, we should concern about FFI in top of the performance. So in their case, we should assume the total number of validator would be 1 million. So this number is not enough, I guess. And also, Lean and Rust has their own memory system or interfaces. So we should concern about these particles. So however, so our goal is not implement just Belty client, but also commit for Lean consensus and any other client team. Currently, Lean spec is implemented in Python. However, we should implement a translation between to Lean consensus spec in Lean, and we can use our asset for implemented is any other CABI clients. Yeah, that and we have a lot of works. One thing is a formal Lean spec, as I mentioned before, this Lean consensus spec part. Also, we try to formal verification to prove safety and liveness for goldfish or simplex, which is a part of the decoupled consensus. And here is a POC for running a GKVM guest program in Lean. If you're interested in our client team, you can scan this QR code. Yeah, thank you. That's it.
Thank you very much. Do we have any quick single question maybe, whilst we switch over to Julian next? And then Julian, if you want to start sharing.
It's Petter actually giving
Not
this.
quite Julian, but close
Petter,
enough.
Yeah, Petter is actually giving this talk. Sorry, please.
Yes, so I think, well, I will send a request for sharing because
Can you try again?
it is fine. Yes, now it is fine.
Perfect.
And now you should be able to see this. And now it might even be full screen.
Yes.
It is. All right, off to you.
Okay, so Petter hi. Hi everyone, I'm Petter from Netmind Security, and I'm going to talk to you briefly about our work on formal verification of various Plonky 3-based RISC-V ZKVMs. So what have we actually done? We have verified opcode soundness for a number of RISC-V ZKVMs against the official RISC-V specification that has been extracted to Lean as part of an EF-funded effort by Galois, Lindy Labs, people in Cambridge, etc. And so sort of the statements that we prove are of the form, if the extracted constraints hold, then the chip that represents a specific RISC-V opcode actually models this opcode behavior correctly. And we prove that there is an equivalence between this opcode behavior as per the ZKVM and the opcode behavior as per the RISC-V specification. We have done this initially for SP1 Hypercube together with Succinct, and I think there will be more word on that later on, where we verified 64-bit SP1 Hypercube. And then we've continued on our own to verify the 32-bit version of OpenVM for Axiom. And our latest project is the verification of both 32-bit and 64-bit Pico for Brevis. The Succinct Labs and Axiom verifications are open source. The Brevis one will be open source the moment Alex says it is okay.
It's okay. I approved it yesterday.
Then it will be open source very quickly. Very shortly. And sort of as a bonus of all of this development, we have built sort of on top of the official RISC-V specification a very simple characterization of the behavior of RISC-V opcodes in terms of only a few basic operations. And that means that for like future proofs against of correctness against the RISC-V spec, all that one needs to show is that basically whatever it is they are doing behaves sort of emits an equivalent like version of these operations. And these operations are very simple, like read register, write register, read memory, write memory, and it abstracts the a lot of the gory detail of the RISC-V spec. And sort of not quite separately from that, but kind of in parallel, we were developing, with the help of another EF grant, Certiplonk, which was meant to be a framework for general reasoning about Plonky tree circuits, where we've created some sort of reusable infrastructure that allows us to extract constraint systems from Plonky 3. And we are still working towards figuring out what would be a unifying interface for sort of extracting information about lookup, permutation, memory arguments. So, and some of the work done in Certiplonk is kind of in the verification of the ZKVMs that we have done, and vice versa, as these projects were kind of intertwined. But yes, so this is sort of what I have. Thank you.
Great, thank you very much. And yeah, there's a hour-long talk about the Axiom and Brevis work that people can find on YouTube. I'll put a link to the YouTube channel that has this towards the end of the session, or someone can put it in the chat now.
Excellent.
And then, yeah, after this, we've got James from OSA, who will talk a bit about zk-lean.
No, still sharing. You all see this?
Yes.
Okay. Yeah, so I'll be talking about zk-lean. This was joint work with some of my colleagues at Galois, as well as Lisa and Carl. There's a link to the repo, so it's open source if you want to check it out. So yeah, I guess the goal of zk-lean is that we want to formally verify the correctness of zk statements. So the approach we took is building zk-lean, which is a lean core library, and that allows you to easily and nicely encode zk statements. So the language supports many zk features that you would want, such as like RNCS, hierarchy constraints, lookup tables, MLE-based lookup tables, and RAM. So like there's like a very simple example of like what a circuit looks like in zk-lean. So here, you have a lean function that's witnessing a new circuit variable, and then it constrains it to be 0, 1 by having this expression x times x minus 1 equals 0. Yeah, and we put in a lot of work to make it composable. So you can see that we have this like zk builder monad that's also abstract over the field, yeah, it's also agnostic to the backend proving system. So we have a lot of integration built into zk-lean to integrate it with other projects that you might want to actually verify properties about. So one thing we did is we built a custom extraction from Jolt. So we have a system that automatically extracts all the lookup tables in Jolt. It will extract it into zk-lean. And then from there, we're actually able to like verify all the lookup tables. So basically like all the instructions and all the opcodes for the 32 RISC-V instructions in Jolt. The other thing we've done, which is more automated and hopefully will be more useful for other projects if they want to use it, is we've built a LZK backend. So on the right-hand side, you can kind of see this diagram of what the architecture of LZK looks like. So you have a bunch of front ends that produce ZK statements, and then you have a bunch of backends that consume ZK statements and do different things like witness generation. So we've implemented a front end. So that means like if you have your circuit written in zk-lean, you can give it to LZK, and then LZK will output all these different representations. And then we've also implemented a backend where you can take your circuits written in Circon or SP1, give it to LZK, and then LZK will output the zk-lean itself, and then you can start doing your verification on your statements. So I'll just go over a quick case study that we did. So this is verifying Ketchak. So on the left-hand side, you can see kind of a short excerpt of what the Ketchak implementation looks like in zk-lean. You have your state at the top where you have all your lanes, and they're all field expressions. And then on the bottom, you can see you have this monadic round function, which is one round of Ketchak, where then you call the subfunctions of theta, rho pi, chi, and iota, which are all the pieces of the Ketchak round. And then on the right-hand side, this is the actual statement of soundness for this function. Basically, you have these for triples, which allow you to define preconditions and postconditions. And basically, this is saying that the circuit implementation over field elements matches the bit vector representation. And then you can see the proof is pretty nice and compositional. All you need to do is you can call basically sublemmas for each of the subcomponents. So you can see we're calling the theta soundness lemma to do this proof. Yeah, so that's it. Happy to take questions.
Thank you. And so Lisa is going to follow up with some work that's related to this. So while she's setting up, if anyone has a question for James, feel free. And then obviously LZK will have its own little talk later on. And if not, then you can go ahead, Lisa.
Great. All right, can you see my slides?
Yep.
Great. All right, so I'm Lisa. I'm a first-year PhD student at Stanford University, and today I'll be talking about BitMoDQ, which is a tactic in Lean for automating verification of zero-knowledge proof arithmetizations in Lean, and is a tactic that we built while I was in an internship at Galois. So as James talked about, like ZK Lean, we want to verify ZKVMs. And one of the issues when we go to verify the arithmetizations is that we really struggle to verify that the bit vector and finite field encodings actually match. So what I mean by this is when we look at the Joe polynomial encoding of a bitwise OR over a finite field, we might have something like this, where we have a BVOR of 2 bit vectors. And then we want to show that the field representation using bits, using elements in the field that represent bits actually matches. And so the issue is existing automation both in Lean and SMT fails. In Lean, it fails because there's a lot of tactics that reason about 2 types. And then in SMT, we have Fury combination, which doesn't, 1, not all the decision procedures produce proofs. And then 2, in Fury combination, the encodings are so tightly coupled that it's hard to solve the problem. And so the insights that we had by looking at arithmetizations is that they don't often contain finite field reasoning. So there's no inverses or 0 divisors, which means we can actually translate to bit vectors and then use existing bit vector procedures. And additionally, if we have a good range analysis module, we can give smaller bit widths, which means that the decision procedures for bit vectors will be more efficient. So we did exactly this. We designed a pipeline to translate from finite fields and bit vectors to bit vectors, and our own custom analysis range module. So we have a 2N pipeline that uses range analysis to apply different rules that translates it to natural number and bit vectors, with natural numbers as an intermediate representation in Lean. And then we translate it to bit vectors, and then we bit blast. And this tells us if our arithmetization is sound or not sound. So we analyzed on both Jolt and Cersei. And what we saw is that one in Lean, there's absolutely there's not even anything to compare to. But for SMT, we do a lot better than them on more complex arithmetizations, which are the ones used in practice. And so this project, we also found 2 bugs. One was in the Jolt Lean extractor, and the other one was in the Cersei compiler itself, which had some issues with Rust overflow semantics. And further, this project has been integrated into ZK Lean and was also accepted as a paper to CAV 2026. So if you're dealing with a lot of bit vectors and finite fields, potentially this tactic could be helpful for you. That is all I have, if anyone has any questions.
Yeah, thank you very much. Congrats on the paper. So I'll switch over. I guess I'll screen share for Gregor's presentation. If anyone wants to quickly unmute and ask a question whilst I do that, feel free.
So very nice work. Do you have a connection to SMT Lean? I don't know what the status of the project is, but it's yeah.
Yeah, it's produced by my lab, and we just actually submitted a paper with finite fields proofs. So now it should support finite fields, which is kind of cool.
Nice.
All right, so I've got my screen share, I've got Gregor's slides, and so the floor is yours, Gregor.
Cool. Yeah, hey. Hello, everyone. I'm Gregor from ZK Security. I'll be presenting Clean, which is our framework for verifying circuits in Lean, which was supported for a long time by an EF grant, and now is developing on its own on various fronts. So I think the best way to convey what it is and how it's useful is this code snippet. So so clean is in trying to do something similar to maybe zk-lean and CircuitPlonk that we heard about earlier. So it's it has a DSL in Lean to express circuits. So if you look at the code, there is a definition is 0, and it has this main field, which is the actual circuit implementation. So it's a classical circuit that computes a Boolean that says whether an element is 0. So you have a witness command that creates this inverse of x. Then you have this constraint equal command that creates b, which is the Boolean return value, and then a final constraint. So in total, you have two RCS-like constraints here, or two arithmetic constraints. And then below that, you have a spec, and that spec says what this circuit is supposed to do. So what the meaning of this circuit is, or you can also call it a postcondition of calling this circuit. So the spec says that B is 1 if X is 0 or 0 otherwise. And then there are two proofs, which are soundness and completeness, and both proofs complete in one line in this example, because I want to stay on this slide a bit, because the proof is very simple, and we have some automation that's designed to make simple things quite easy to prove. So one thing to note here is that we're currently changing our witnessing approach. So it used to be you could witness an arbitrary Lean. Your witness generator was an arbitrary Lean function, which gives a lot of flexibility, but it's not very good for exporting. So we are switching to a sort of IR, deep embedded in Lean, to create a witness generation code, and you can see that in this .ite if then that's a sort of if then else. Yeah. So there's basically two DSLs you can see here. It's one for the witness generation code, and the other top level DSL is for the constraint definition. So the nice thing about this is that we have a completely symbolic representation of both the constraints and witness generation code, and we can, from this definition, we can export to a fast implementation, possibly a GPU implementation or a Rust implementation, and it's very easy to write this printer that takes our constraints and witness generation AST and converts that to, for example, Rust code. So the goal here is to have give you a framework to write circuits that are sound and complete by design. So it's more, I think of it more as a front end than as a formal verification backend that you extract stuff to. So maybe one step back to make another point. Alex, can you go back?
Yep.
So I think one other point that I want to make here is there's a soundness and completeness theorem, and it's the same for every circuit. So in a lot of the extraction pipelines, you see basically you prove ad hoc theorems, and Clean really tries to be a framework that gives you a single definition that says what it means for a circuit to be sound. So everything you do has to fit in that framework, and so basically you never have to. You only have to check that statement once, and once you're convinced that this is a good definition of soundness, you will never have to think hard about what is actually proved, and for every individual circuit. So the only thing we really have to look at is the spec here to convince ourselves that this is doing the right thing. And some circuits have additionally have assumptions on the inputs. So you would look at the assumptions and and on the spec. And here the spec is often really simple. So you often have huge circuits with thousands of witnesses, and in the end they just prove a scalar multiplication, and the scalar multiplication spec is like just one line. So you're reducing a huge amount of complexity to just verifying that something very simple. Okay, next slide. So to summarize the goals that we have here. So we wanted to look pretty, so we wanted to compete with the existing front ends like Circum. So I want Clean to be a drop-in replacement of Circum, for example. With the difference that the circuits are already formally verified from the start. So the whole all of the trouble we have with auditing circuits is just going away. Then we really try to make the proving UX good, so that's what I call PX. So it should be once you're dropped into your soundness proof, you call our tactic that starts the proof, and that should do get rid of most of the boilerplate of our framework and give you the actual mathematical statement to prove. That's really the strong goal. There's still more to do on this, but I think by now we've scaled to pretty complex circuits, and that shows this is pretty feasible. So we implemented real implementations of stuff like Ketchup, SHA-2, Lake, and our latest are also small VMs. And so these show that framework scales. The proofs don't get too complicated. Also, we found that LLMs are pretty good at creating insight.
Yes, and? Okay, I'm aware.
Thanks for muting. All right. So yeah, then Clean very much wants to be exposing the raw constraints and the non-determinism, so it should be on par with other low-level circuit DSLs. And because it's just embedded in Lean, you have a really powerful general purpose language to do abstractions. So for example, you can create higher level types like I don't know, curve point, or a multi-limb begin and stuff like that. You can create your own abstractions because you're in the end you're just writing Lean and not any custom language. So yeah, that's our goals and our ongoing efforts where we are right now. So the latest big chunk of work was that we started modeling entire CKVMs in Clean. So what you saw before was one circuit, one formalized circuit, and what a VM would be, it defines multiple air components, and it also defines cross-table interaction channels. And then, can you still hear me? Okay. And then you define a whole system of airs that implements the CKVM, and then you prove that sound in a global view. So we have like a proof of concept of this. We recently added padding, so padded interactions. So it's becoming more and more like modeling real world systems. So I think in the end we will be in a place where you can define your entire CKVM in Clean that is not behind on any metric behind like the production CKVMs that are often written in Rust, and it's completely end-to-end formally verified, both the soundness and completeness statement. Or I mean, I should be careful when I say end-to-end, but talking about the air and circuit statement, that will be completely end-to-end verified. Despite like not verifying the proving backend. Then other efforts. So we're currently formalizing the Zcash Ironwood circuit, which is probably the largest project we've done so far. And we already have a complete proof of concept. So, and this was like written in a rush to help the current Zcash efforts for verification. And it was written like in 2 weeks with heavily LLM assisted. And this was really a confirmation that this whole idea kind of works. Because yeah, I didn't have to read thousands of lines of proofs to convince myself that this is actually formalizing the correct spec of the Zcash circuit, of the action circuit. And we will continue this effort. Right now, it's sort of approximating the Planck arithmetization, and in the coming weeks, we will make that like a proper model of Planck that can really match the verification key on the Rust side 1-to-1. So it has to model like the custom dates and the column layout and everything. So we will in this effort we will kind of generalize Clean. Currently, it's more designed for airs and R1CS. But I really want, in the end, I want it to be sort of a circuit DSL for everything, general enough to cover everything. And we will very soon, TM, release a circuit optimization challenge, so which will be called ZK Golf. So look out for that. This is sort of an experiment because we found. So some of our engineers have been playing with Clean without knowing much about Lean, and like my co-founder just told Claude to write like the most optimized SHA-2 implementation in R1CS, and it did it, and it created something which is much more efficient than any of the production circuit libraries, and it's already formally verified, so you know all those optimizations work. So that's why we call it fearless optimization. And we want to create a bit of a game around that, put up a website where there are different challenges for circuits to optimize, and people can submit them. It's going to be a bit like ECDSA.fail for improving the Google post-quantum circuit. So yeah, that will be fun. Look out for that. Yeah, so that's it for me.
Thank you. So I think, so this covered the kind of Ragu slots because we didn't get confirmation from the Zcash fork, but then we can follow up straight away with Devin. I'll open your slides as well, who also has some Clean related work to talk about. So off to you, Devin.
Yeah, so, sorry, I don't know if the ping is the best format for this, but yeah, so I guess Gregor just talked about Clean, and yeah, we had already an existing sort of soundness verification of SP1 that Peter had talked about, and so we have this soundness, but it's sort of a mess, and it's not exactly very modular or easy to sort of keep track of everything that's happening. So I guess for quite a number of reasons, we switched the actual DSL to Clean. And so on the top here, I have just sort of the general pipeline we're using for this. Like Gregor said, the Clean sort of functions better, I think, as a front end. So what we actually do is extract the constraints and the interactions from the Rust and prove faithfulness, so some equivalence between the interactions and constraints in re-implementations of all the circuits in Clean. This lets us sort of change the circuits in slight ways that make proofs easier without affecting the Rust, and still knowing that things are, actually modeling the proper code. And then instead of bridging directly to Sail, the big complicated monadic model of Sail, we write specs for each Clean circuit in terms of pure RV64 specifications. So it's just making pure statements about arithmetic or a number of interactions and things like this. And then on top of the soundness proofs, that was reused as much as we could from the work that done with Nethermind. We also now have completeness for each chip in the other direction from these specs. And then we show this pure RV64 specification gives us most of this bridging to sale already, but we do need to sort of tie and wire a bunch of things in to eventually show then that also on the monadic sale, we also preserve the constraints. So in the end, we get stronger guarantees than we had before. It's a lot easier to read the proofs. I think total size of the code base went down, I think still, depending how you measure some of the tests. And it compiles a lot faster. I think there's been, I would say mainly just upsides to this. I would strongly recommend not rolling your own DSL at this point. There's also some in-progress work on doing full trace level things, the full ensemble soundness and completeness. The soundness is mostly done, the completeness much less so. And then having a full end-to-end theorem. And then on the left down there, I guess I have kind of just what the circuits generally look like. We have just a number of assertions, usually some witnesses. We're still using this old version of witnesses. I know whenever Gregor gets the new version in, we'll have to change all that. But we're verifying it correct relative to those, and then for each thing we have an assumption in the spec that looks something vaguely like this. Yeah.
Thank you. Very cool. And I can confirm it does actually build quite a lot faster by an order of magnitude, probably. All right, so then we have Albert's talks. I think, Albert, you wanted to share if it works. So if you want to try and share, I'll let you share. And if it doesn't, I'll switch over to sharing again.
Can you see my screen?
Yep.
Yes. Okay, so this is Albert from the Costa Group.
So your volume is a bit low. I don't know if you can up your microphone volume or speak louder.
Is it better now?
Yeah, that's better.
Yeah. So this is Albert from the Costa Group at the Complutense University from Madrid, and this is research funded by the Ethereum Foundation. So our aim is to develop the Abazzar tool, fully automated tool to help developers to easily find bugs or to have a first good level of confidence on the correctness of their ZK virtual machines. And this is done by using SMT solvers. Okay, so the first key points that besides determinism, Abazzar can focus on proving semantic equivalence, which means this to check the equivalence between the witness computation code given in LLZK and the arithmetization, the constraint system. So the first important thing in our tool is that the transformation from the witness computation to an SMT formula is done by using LIN and then provide a certified transformation. So we don't lose anything when going from the LLCK to SMT2. I mean, don't lose anything regarding the correctness. And then the second important point is that we have developed our own open source SMT solver, which focus on ZK verification properties. So this solver use several light checkers to avoid the heavy reasoning on finite fields, but also includes range check reasoning natively, which has turned out to be very useful when proving properties of ZK virtual machines. In particular, although we have a portfolio of solvers and other tools, it's almost the case that our solver is the one that solves the SMT problem. So regarding the evaluation, we have evaluated our tool verifying THISC as our case study, but we can apply to any other tool. In fact, if they can provide LLCK, we can apply our tool. And we have done it for recursion circuits and for state machines. And for recursion circuits, we have proved determinism, and we found two bugs. And once they are fixed, we were able to verify it automatically up to 90% of the circuits. And there were some that the reasoning was beyond what an SMT solver can do, but this was really tiny. And then for state machines, we have considered determinism. We have verified all binary machines, and we are working on the arith, and then we will go to the memory. And for semantic equivalence, we have applied the full pipeline to prove fully automatically the equivalence of the binary add, and now we are with the rest of the binary machines. And also we have applied this to prove semantic equivalence of circuits from the circumlab. So all this can be found in this Git. It's all open. And if you have any problem to install it, or you want to know anything else about it, just tell us. Thank you.
Thank you very much. If anyone has any questions, you can quickly ask one, and then I'll share for Cody. Oh, yes, and there's a timer button. Perfect. All right, off to you, Cody.
I still see Albert's slides.
Oh, sorry.
Yeah.
I'm not sharing. That's better. Okay, off to you.
But now, okay, yeah. Yeah, thanks. So yeah, we could go to the next slide. I'll share a link after I finish speaking. So my goal was to do a RISC-V for spec verification effort for ZISC, which hadn't been done. I had a good starting point from the work of Petter and others at Nethermind and friends. So I thought I would begin as a sort of passive experiment, and then if it started to take form, take it more seriously, and that's what we have here. I think it's in decent shape now. I guess you could just advance all the bullet points, Alex. Thanks. Since you're sharing. Yeah. So yeah, I mean, the goal is to initially show soundness. So to show that the state transitions accepted by ZISC are spec valid, and well, we've heard these terms already, so maybe I can go on. I wanted good reproducibility of everything, including the extractions and good CI turnaround. That's all in a good place. I wanted to use standard tools like Aeneas and Clean, and to be explicit about the verification boundary and claims, and to implement testing to cover those gaps. So we can go on to the next slide. Thank you, and maybe just go through all the bullet points there too. Right, so the goal was to sort of build it end-to-end, allow the AIs to axiomatize and then remove axioms. And yeah, I could tell that it was working because I found bugs. I found 3 bugs in ZISC doing this. So 2 of which were new to them, and 1 that they had between the time of me starting the work on version 0.17 and them, and then a couple of upgrades later, they had found that other bug. So now I'm in the process of like cleaning it up, making it more legible, and then I'll audit it a bit with Hector from ZISC, and then perform some upgrades to test maintainability, think about maybe the structure of the FV library in those terms, and then work on completeness and expanding testing. So that's all for me. Thanks.
Thank you. And then I think next we have Kwong, who I think is going to share.
Yes. Give me one minute. All right. So, okay. So my slide is on the it's on the Google Drive, but I also share it here. Cool. Can you see this?
Yep.
All right, cool. So I will be doing double duty here and talk about both VCVIO and RClip. So these are 2 lean libraries. Oh, let me see. Cool. So these are 2 lean libraries for the efforts of formally verified proof systems, aka the Starks that we know and love. In order to do that, we first need to have a base layer for reasoning about cryptography, and that is VCVIO. The job of VCVIO is to define this base layer based on the notion of oracle computations or algebraic effects. We give it the semantics that is probabilistic. We give it a program logic that can reason about both a single program or a coupling of two programs. We also have a bunch of examples, including the NIST standardized lattice and hash-based signatures. These are ongoing works. Some other works like the forking lemma has been finished. And we have downstream usage now beyond just ArcLib. There's a project using ours to do symbolic cryptography in Lean. There's another ongoing project called SignalShot that's trying to formally verify the whole of Signal protocol, and they use VCVIO to scaffold their definitions. Now, let me come to ArcLib, which is the main library that I think people care about here, about formally verifying our Starks. At the core of ArcLib is the notion of interactive oracle reductions, or IORs. We define what they are, and we define how they can be composed. The main motivation here is that Starks are fairly complicated, and so we should be breaking them down into modular components, specify them, prove the security, and then compose them together. And the composition theorems will say, if your components are secure and the glue is secure, then the whole thing is secure, roughly speaking. We're also starting to really ramp up the work on the Fiat-Shamir transform. This is not just a theoretical kind of transform, it is the actual transformation that is used in the SpongeFizz library, and that is also going to be set as an IETF draft. I think there will be a later talk here that will talk more about this. We're also starting to have links to other libraries, say for the front-end verification or for verifying Rust code bases. And we have ongoing examples, including the Samcheck protocols, a bunch of polynomial commitment schemes that are both hash-based and more recently also lattice-based schemes. And one very exciting news that just happened, I think, a day ago is that ArcLib is now featured as one of Lean's use cases alongside MathLib, CSLib, Alias, and so on. So it's a very exciting time. And if you're interested in contributing to either of these libraries, they're open source. You're free to give us PRs. We would greatly appreciate them. Thank you.
Thank you. And we get, I should say, we do get quite a lot of PRs and a lot of first-time contributors. So thanks to everyone who has submitted PRs that we've merged or not merged. We appreciate all PRs. Okay, so next we're going to have Baz and then Derek. I will share for both, so in the interest of keeping myself muted, I'll let Derek chime in as soon as Baz is finished, and I'll just start sharing now.
Yes, thank you. I want to present CatCrypt. So this paper's been online for a bit. So it's a large library in Lean about cryptography in the computational model, inspired and partially started as a port of the Ethproofs library that we have in Rock, which is a big library based on state separating proofs, which are very appropriate for protocols that share state. So this is the methodology behind, for example, the Joy of Cryptography book. And so that actually carries over very nicely. It's called CatCrypt because there's a big categorical treatment behind it. So we have a categorical treatment of universal composability and of the state separating proofs, and they're nicely combined in the library. It's all built on, we also have a bridge to the high assurance primitives. So we have a huge library of elliptic curves. So that's in Rock, but I can translate them to Lean via a shared Rust subset. So that code is online. it also contains quite a bit of the Dalek library that already includes fiat crypto backends, but now we verified much more in ROC, but I can translate it to Lean. I've translated most of that to Lean. So that has a full suite of elliptic curves. Some of them are the first implementation. It's connected to our Hex tooling. So we have two embeddings, both in the imperative and the direct functional embedding. So for all of the protocols, most of the protocols in CatCrypt, I actually have a reference implementation in Hex. I can also target some of the other libraries. And part of the Hex library are verified in Lean, basically the last third. So once you're at the tier level, you do some transformations, and then you end up in a fairly well understood subset. And that subset I verified in Lean. It's tightly integrated into the Lean ecosystem. It's connected to Mathlib, to Arclib, to Compoly. That's the next talk, I think, and to VCV. And yeah, the preprint is online. I'll soon also release the other parts. Thank you.
And I'll add to this, one of the quite impressive things about this is the amount of content that was generated for CatCrypt, which is, it's a review bottleneck, but in terms of generating a lot of content very quickly, it was super impressive. And then I guess we can switch over to Derek, who will tell us about Compoly.
Great. Yep. Let's see, I will present on Compoly. Go to next slide. What is Compoly? Compoly is a library of computable polynomials in Lean. So it started with just univariate, bivariate, multivariate, and multilinear polynomials. We also have a field, I guess, field specification. We have implementations of fields and other kind of algebraic foundations of snarks. And so why do we have Compoly? Compoly is the computable core of Arclib. That's kind of where it started. And it mirrors a lot of the constructions in algebraic constructions in Mathlib, but with computable. So everything in Compoly is computable and then proved equivalent to its counterpart in Mathlib. So you can still do all your proofs in Mathlib by transporting over the isomorphisms. And then there are just lots of applications of computable polynomials outside of Arclib, and so this library is kind of its dream is to be useful all over the place. Next slide. So we've been working on a roadmap with Compoly since the beginning of this year. We finished up with the theoretical foundations phase 1 in March of this year, and that was mostly theoretical and API completeness. Phase 2 is very close to being finished. So I've put the check mark for July. We're just finishing up with some of the fast field arithmetic and implementations, and phase 2 is focused mostly on optimizations, benchmarking, and making these not only computable, but kind of interestingly computable and reasonably fast within Lean. And phase 3 is what we'll be working on over the next several months, is further optimizations and then kind of getting it integrated in the community, hopefully upstreaming to CSLib at some point. Next slide. So we've had a lot of recent contributions. I just wanted to highlight some of the recent work that's been done by various contributors. So we have interpolation, we have barycentric interpolation, we have several root finding algorithms that are specialized in different places. We have bivariate operations, division, factorization. We have a computable Guruswamy Siddhan, which is actually pretty cool. Guruswamy himself reached out to Formaland, who did this work, and may use it with his students. We have various optimizations of evaluation, error correction, fast fields, etc. Next slide. So there's the link if you want to learn more, and these phase 2 contributors, I've listed them here. So yeah, thank you all for all your help. This is very much a community effort. And that's all I have.
Thank you very much. Let me just check the chat quickly. Not too many questions. And so yeah, so this was really nice work. Okay, so now I guess it's for me and Giacomo, so I'll keep sharing and I'll let Giacomo introduce things a bit.
Perfect. Hey guys, so good. So I want to give like a little tiny update about proximity price and how formal verification we think will be a very important tool for like the proximity price verification we're gonna do. So just as a very quick refresher, the proximity price is a set of challenges relating to the security of hash-based narcs, which go and find the roots into coding theory. We have a website, we have like the statement, and we have a companion paper, which is this ABF 26 paper, which formalizes what are the conjecture that we believe and we would like people to invest their time onto. Within this paper, one of the things that we introduced is this toy protocol, which is as in the name, a toy protocol in which there's the analysis closely mirrors that of existing hash-based proof systems. And throughout the paper, we analyze both the knowledge soundness and attacks on this toy protocol. So as a target that we want both for like auto research formalization and for like the proximity price, we would like people to figure out what is the actual soundness that this very simple protocol can provide. And what I'm really happy to say that Alice will talk more about this is that now most of this paper has been formalized into Lean. So now we have theorems and we have like actually verifiable theorems about what is the content of the paper, which we hope can be useful for both, like for the sanity of the judges to figuring out which results are actually correct, and also for like enabling like the wider community to contribute and have confidence in their contribution. So on this note, I'll let Alice tell you a bit more on the Lean side of what has been done for this for the proximity price.
Yep. I didn't have to unmute. Oh, no, I'm unmuted. Perfect. Yeah. So as Giacomo said, basically, I've been spending a bit of time formalizing the contents of this paper on top of RClip. RClip, for background, obviously already had a large body of coding theory proofs because we have the proximity gaps for Solomon codes, for example, is proven in RClip and so on. So we already had a lot of preliminary material. There was a bit more material to add. But this PR here basically contains everything. I think I have 3 small stories that I need to go and address, and this will be done soon. It covers the entirety or pretty much all of the paper and everything that you need to state the actual conjectures and the grand challenge. And so as of right before this call, we have a new repository. It's currently private. It will be made public and upstreamed as soon as I have spent a bit more time reviewing my PR and checking that the statements are actually correct. But we have a standalone repository that pulls in RClip as a dependency. And if ever you think that you've cracked the conjectures, you can open a PR and CI will check it. And we should be able to make progress. There is built-in support, or it's intended obviously to support auto research. We've seen a lot of progress on this with the quantum circuits, and obviously Clean is going to have some auto research. Everyone is doing auto research. We should do auto research for this as well. So it's formulated in a way to support and facilitate auto research. It'll be public very soon. Looking forward to everyone contributing. Yep, that's basically it. And I guess I should say the formalization efforts did find at least some things that led to changes in the paper. I think it was Lemma 612 that changed. And so it wasn't, it was useful, or at least it's been useful already to some extent. And hopefully it'll be useful in helping out sort out solutions to the conjectures. And I think that's it from me. And then we're off to Fiat Shabir, so I can stop screen sharing. And then, yeah, Chang is ready. Off to you, Chang. You muted, Chang.
Okay, can you hear me?
Yep.
So today I present our project formalizing the duplex response via Shamir transformation in Lean 4 and in the RClip library. And our team consists of me, Trung Nguyễn, Michaela Oru, and Quang Dao. So the via Shamir transformation is a critical component in deploy synapse, and it transforms the non-interactive protocols. It transforms the interactive protocols into the non-interactive protocols, and in the theoretical model, it let the prover make queries to the random oracles to get the verifier challenges. And in practice, people usually instantiate it with Sponge construction. And in the paper CO25, a Fisher-Shamir transformation from duplex sponge or DSFS, the authors provided rigorous analysis, security analysis for the Fisher-Shamir variant based on duplex sponges. And so simply put, each round in the DSFS construction, the prover absorb the encoded prover messages into the sponge and squeeze out the verifier challenges. And these two operations, they trigger calls to the a single fixed size permutation oracle, and which is consistent across the rounds. And this is close to what practitioners do. And since we started working on this project, we are about 30% done. We have finished the construction and the soundness proofs. And there are things that turn out to be different when we bring the pen and paper proofs into the Ethereum prover. For example, when we work on formalizing the data structure for looking up the trace entry, instead of following the paper and implementing a specific data structure that is highly efficient, we decided to design an abstract specification class that contains the allowed operation as well as the mathematical constraint for the operation. And this way we can plug in any implementation without exposing the internal logic of the data trace of the data structure into the proof layer, and we can like delay the implementation of the complex and efficient data structure and without blocking the progress. And in conclusion, in this project, we do the formal verification of the duplex sponge via Shamir transformation, and the source code will be available in the Arclip repository, and you can check it on there. And that's all from me.
Thank you very much. And so next up, we're going to have Matthias, who's going to talk about XMSX signatures and verifying these.
Okay, can you hear me and see my screen?
Yep.
Okay, perfect. So, hi everyone. My name is Matthias. And like others here, I don't have yet any cool, amazing results to show. So this is more like a quick introduction to a new project that I am working on, that we are working on. Oh, does it work? Yeah. So quickly, some sort of background, relevant background, related background on me. I've recently finished my PhD, where I mostly did formal verification of post-quantum cryptography using the EasyCrypt and Jasmine sort of Formosa toolchain. Maybe you've heard of those. Yeah. And so particularly I did the hash-based signature schemes, XMSS and Sphinx Plus, both their security proofs as well as their the functional correctness to their implementations. And so then there is this proposal to move Ethereum to post-quantum by replacing BLS by a multi-signature variant of XMSS as a replacement to the aggregate signatures. And so to sort of make use of my experience with the hash-based signature security proof side of things, we decided to, well, try and have a look at formalizing this and formally proving the security proof of this proposal in Lean. And so, as I said, there's not many cool results yet, but the overview of the overall proof and scheme looks as follows. So we have the final scheme, which can be decomposed in like a generalized XMSS, variant of XMSS, as well as an aggregation scheme for signatures, which is just, in this case, going to be a PQ snark, which is left abstract for this scheme. So the focus is mainly really on the hash-based XMSS here. Then the XMSS, in turn, can be decomposed in these components. You have the Merkle tree, of course, the function change for the one-time signatures, as well as the encoding scheme that has to be incomparable. Right, so these are the components of the XMSS. And then at the bottom, of course, you have the hash functions on which everything is based. And so also in this sort of decomposition, I'm planning to sort of tackle this, and starting from bottom up, of course. And so currently I am still looking at these these foundations here, and some of it has already been done, like the basics. But yeah, as I said, no impressive results yet. So hopefully next time in the next call, I will be able to actually give some cool results here on this project. Yeah, and that's it for me. Yeah.
Thank you very much. Let's see if we have if anyone has any questions, and then otherwise, I think next up is Nadim or Hossein or Lorenzo, who will talk to us about SoundCalc and Lean.
Okay, can you see my screen?
Yep.
Perfect. Hi everyone, thanks for the introduction. So a couple of weeks ago, we started formalizing SoundCalc in Lean. We actually started porting it, and very rough again, SoundCalc is this tool that currently allows zkVM devs to have a quick and efficient way to compare, let's say, different configurations some zkVM may have. What happens if we switch fields around? How does this affect soundness, and whether, again, the overall soundness that one gets still is within some provable bound. Yeah. So why bother doing that in Lean? Well, crucially because, again, the current implementation is in Python. There could very well be implementation errors, saying hand transcribing formulas. There could be bugs in the formulas that may not be linked to the underlying cryptographic assumptions. And also, it could very well be the case that some Python artifacts may lead to some loss in accuracy, say, whenever we're dealing with evaluating exact arithmetics or reasoning about rational numbers, for instance. And indeed, here you can see a couple of examples of semantic, let's say, mistakes that were done in on inaccuracy rather that were done in the current SoundCalc. For instance, we have a rate that is weakly cast to an integer as opposed to a float, and on the right-hand side you can see that this list size parameter, which should increase the error, is actually decreasing it in a specific zkVM configuration. So with Lean, basically, we are aiming at providing a SoundCalc on steroids that at the bare minimum matches the current SoundCalc evaluation, so that we get a one-to-one match with respect to the reports that are currently being produced by the current project, but also having a verified calculation on top, so that, yeah, if there is any issue, any discrepancy between the two, we can actually figure out whether we were wrong in formalizing it in Lean or whether there was an inaccuracy in the original SoundCalc. And once we have this foundational building block, this solid building block, we're planning on actually building useful tools on top of that. We are aiming at providing also a way for developers to prove theorems that could be stated in a way like, I mean, if I switch a field with another field in a specific configuration, I'm not going to lose security, and I can prove that. And we're aiming at the bare minimum to have A plus B by the end of the internship. And then there is step C, which is much more open-ended, which aims also to have some kind of integration with the current ecosystem, with Arclib and the latter, so that indeed all the formulas that we have in Lean can actually come with a companion theorem that could allow us to say, for instance, that a specific item, a specific component of the zkVM soundness error is indeed bounded by a formula under some small and shrinkable trusted ledger. That's that. So stay tuned.
Thank you very much. Yeah, I think this is pretty cool. And in general, like being able to do some statements over some composed proof systems. This is what zkVM uses, is something we've been after for a while. So very much looking forward to this. And then next up, we have Raul, who's going to talk to us about the work on translating Veil, which is Succinct's kind of compiler to make proof ZK, and obviously doing some proofs about this in Lean.
Okay, so everyone can hear me and see the screen? Perfect. Okay, so let me begin. Thanks to everyone for coming to this and listening. So first of all, as you heard, I'm talking about formally verifying a particular practical protocol. So this is a Succinct's Veil compiler, which is basically a compiler that you feed in an example of sort of a broad class of cryptographic protocols, and it adds hash base, so plausibly post-quantum, zero knowledge to this protocol. So Veil is optimized to have a low engineering and performance overhead. So if you've coded up your protocol already, it shouldn't take that much more code to convert it into Veil. And the prover for the new protocol should be negligibly slower than the prover for the old protocol. So we're actually going to be using this. We're trying to convert SP1 into the Veil format so that we can have sort of a post-quantum zero knowledge added to SP1. So Veil has a big problem, and the big problem is that the proofs of soundness and ZK-ness depend on 30 pages of dense and very finicky mathematics. And in particular, ZK-ness is notorious for being very easy to make mistakes with, particularly for practical protocols that have all the fiddly details that you need for to handle all the use cases. So because of this, we felt that we needed a better guarantee of protocol correctness than just maybe human written proofs in a paper. So how did we get this? Well, miraculously, it turned out that modern LLMs, with them, it's very effective and practical to actually prove ZK-ness, or to verify protocols. So we were able to use to use Claude Opus 4.6, 4.7, which use human written proofs as a reference to generate a formal verification in Lean. This did not take any sophisticated harnessing, just the Claude.md that kept a running record of common writing pitfalls that we found the AI doing and things like that. And the total human time was basically the equivalent of just 1 to 2 person weeks of full-time work. And frankly, it was only that much because of maybe like my lack of Lean experience before this project and some stupid mistakes. So this was very efficient. So the key difficulty of this is that it was very hard to get a correct sort of trusted base. You have to make sure that you're actually verifying the correct thing when you're working with Lean. So this took dozens of iterations of human-directed edits for correctness and readability, and it required very careful human auditing. So it was very important that we had a good interface to audit these protocols, to audit the formal base of formal statements properly. And once this was done, the proofs were very straightforward. They were basically one-shot. And as everyone else has been pointing out, a test of usefulness is that we actually caught a ZK bug. So in conclusion, I think this is like a very effective way to sort of add more guarantees that a new protocol can be correct. And I think this is a thing that sort of more people should try to do. Thanks.
Thank you. And then I think, so that finishes the, I guess, cryptography section. And so next up we have, I guess, a bit of an interlude with auto research that Bana is going to talk to us about, and then we'll go into compilers for cryptography. So off to you, Bana.
Okay. Can you hear me well?
Yep.
Perfect. So for the past 3 months, I have been applying auto research as a methodology for zero knowledge code bases. And on the left, you can see a little bit of my harness that I have been using with many supporting personas to enable the auto researcher persona to work. On the right side, I brought a little practical example. I believe smaller models are the perfect sandbox environment for building these up, because you run into issues that also exist in a larger model, but they are abstracted away. So this specific example was research discipline, which was a big issue on Opus. I implemented some hooks to enforce the behavior, and then it produced quite outstanding quality directly on Fable for the few days that it was up. In terms of results, this was mainly targeted at the LeanVM code base. The coolest PR, I think, is the ZK alloc PR that I highlighted. This was a bomb preset arena allocator reusing like a technique from the 90s that produced the 27% speed up for warm proofs on the native prover side. And what's actually really cool is that the previous PR before that was about eliminating alloc contention, which already produced the 10% speed up on the native prover side, but there was still overhead to find. next to that, we also contributed with this to Plonky3, Ignore, Crypto, and Vortex with smaller amount of PRs. And the missing piece was essentially quite obvious during the ECDSA.fail initiative, where the ZK proof that was published for Google's quantum circuit acted as the perfect invariant to essentially let the agents perform really, really well. And the equivalent is for ZK code bases, it's obviously formal verification. Beside that, I have been experimenting in the last weeks with automated auditing processes in loop and out of loop. And you can check out the work on my GitHub. The repo is open source.
Yeah, thank you. And yeah, there's been already some interesting lean results that have come out of this, which is very, very cool. So we can go into compilers then, starting with compilers for circuits with LLZK. I'll let Veridice go in.
All right, thank you very much. All right, so we are working to bring formal verification tooling to the LLZK-IR, which is our shared common intermediate representation for ZK circuits, which is implemented using the MLIR compiler framework. So one problem that we've recently been working to tackle is that of circuit inconsistencies between witness computation and constraint generation that can lead to security vulnerabilities that are hard to uncover during audits. Our goal then was to build a verification tool that could automatically verify the consistency between the witness computation and the constraint generation. This led us to develop a tool that we call LLEQ, which uses a combination of lightweight static analysis and deductive verification to verify if witness logic and constraint generation logic are equivalent. And we plan to have a dedicated talk about LLEQ this coming Monday on June 29th. Another problem that we've tackled recently is that of encoding formal semantics in ZK circuits, which is currently challenging as developers must write custom libraries for general purpose proving languages to encode ZK specific properties. Our goal then was to allow developers to specify formal properties of ZK circuits independently of the target proving language's low-level details, while also integrating seamlessly with the rest of the ZK ecosystem. And this has led us to develop LZK spec, which is a high-level specification language targeting compiled LZK IR circuits, and then the verif MLIR dialect that LZK spec compiles into and can be further lowered into SMT for verification tasks. We actually recently had a dedicated talk about this project this past Monday, and you should be able to find the recording for this on the Verified ZK EVM YouTube channel, at least at some point. The LZK ecosystem has already supported production-level verification tooling as well, as Veridice has updated our in-house determinism verifier Picus to use the LZK IR stack and has recently found 7 real-world soundness bugs over one weekend of verification effort. And so you can find the suite of projects and more under the open source Project LLZK organization, and we look forward to engaging with you as we continue our mission to formally verify ZK systems. Thanks, and I'll take any questions that you have.
Yeah, so if anyone has some questions whilst we switch over, feel free. And yeah, the talk Ian mentioned will be up on YouTube probably later today. I need to go and fetch it from the Google Drive. And so next up, we've got Gerion, who's also going to talk about, I guess, constraints, but in the context of auto precompiles this time.
Hello. Yeah, so this is, I'm Gerion. I'm talking about translation validation for Powder auto precompiles. This joint work with Ari and Alex. Ari and I are working at Satara. Alex just started at Georgia Tech. So as we weren't quite sure how familiar people are with Powder, I'll just take half a minute to talk about that. So Powder takes basically the KVM semantics, so and for example, OpenVM program, and compiles it into a big program, ZK VM program for the OpenVM program. And this first step is just basically structurally meshing together pre-built gadgets. And this is, I mean, I think we already heard a bit about how to prove correctness for these gadgets, so for single instructions, but then the step is pretty much correct by construction. And then the idea in Powder is that we're doing a big optimization pipeline to make the knowledge proof in the end, or the constraint system, much smaller. And this is actually a lot of individual rewrites, more or less complex, and in principle, a lot can go wrong there, as we know from regular compilers. And so we want to, the goal of our project is to figure out whether we can formally verify what happens in this auto precompile pipeline. And so what we do is we take a concrete program with Powder, and then we verify that the equivalence for each individual optimization step. So it's we don't directly verify the pipeline in Lean or anything, but we do translation validation for particular inputs. So what we did is we first formally defined a notion of I/O equivalent with bus interactions, then implemented that. It reduces to SMT, and we eventually solve that with an off-the-shelf SMT solver, currently Z3, but yeah, whatever performs best, obviously. Between that, we do a bunch of domain-specific simplifications where the domain can be just the domain of ZK, but also what exactly the Powder optimizations are doing, and also how exactly our notion of equivalent works. And then we're evaluating that on the 3 benchmarks the Powder team told us to be most relevant to them. So that would be Ketchak, pairing, and Ref. So we found a few minor issues that the Powder team already knew about, and we kind of then told them, yeah, how about you actually prioritize that. So we didn't really find anything big. So this is probably a testament to the good code quality of the Powder code base. To note here, that verifies the correctness of the auto precompiles optimizations. It does not say anything about the programs that actually go into Powder. So if you give Powder an incorrect input, then the output will be incorrect as well, just as for the compilers. So the future work is we want to emit proofs, because in the current model, essentially all of our tooling is part of the trusted code base. So if we tell, yeah, it's correct, you need to trust us. So we want to make that proof producing so that you can then feed that into Lean, and we basically just provide a witness that you can verify. Yeah, and currently it's more or less in a prototype stage, so we want to scale that up to bigger examples. So on the right-hand side, we have the current state of the Ketchak benchmark. As you can see, we have like over 90% of the steps verified. Over 70% of the basic blocks in the whole program are fully verified. But you can see in the graph there are a couple of blocks that are just huge, and we just currently die in our initial encoding just because it's a prototype Python implementation. We're currently working on that. And just to get a feeling on how long that takes, so the average verified time from start to finish is 31 seconds. So that's not just SMT solving time in the end, it's complete us loading the dumps, analyzing them, creating the encoding, simplifying it, and solving it. That's it for me. Thanks for the time.
Yeah, thank you very much. And I think auto precompiles are used obviously by OpenVM and SP1 who are both interested in using it. So there's some nice immediate applications to this. Okay, and then next up we've got Manuel from Lambda class, who gave a fantastic talk about AMO Lean, which is an optimizing compiler for constraints a while back, and he's now going to talk about Superhash, which is some more recent work.
Hi, everybody. Do you see the screen?
Yep.
Hi, thank you for having us. My name is Manuel. I work at Lambda class in Buenos Aires, Argentina. We're going to talk about our progress in TRC. TRC is an idea of applying eGraphs to the design of hash functions. So the basic idea for people that haven't heard the previous talk is that hash functions can be thought of as compositions of atomic functions. In a more maybe computer science way, you can model a hash function as an AST. And at this point, we're working in a very restricted vocabulary. That is that we are using S boxes and linear layers to compose and design hashes. And one of the things that we've been doing now is we're trying to tie that design to an executable hash. That means that we need to transform the abstract design to something that actually runs. And for that, we have a theorem that we're actually running the correct design. The E-graph that will work with the design is something that works in a mathematical way. So in that sense, all designs are actually equivalence classes of designs. And the saturation part in which we can pick an optimal design is a mathematical extraction. Since we're restricting to a small class of hash functions, we have built this pipeline end-to-end for some reference hashes. This is a very small set, and we can actually run this for 3 specific hashes, but not for all the designs. That's a work in progress. We have like the building blocks, and we're going to wire those blocks in the future. Then we start to work in the comparison of the designs. And since a design has an associated parameter vector, we need to be very careful on how we see each of those parameters, mainly because different families of hash functions mean different things when they say active S boxes or solving degree. So what we need to have is a fair comparison between families, mainly because those notions that come usually from solving Robner basis problems usually mean different things. So our approach is to build a pipeline that can fairly compare those vectors. Designs are not compared directly, but they're compared through their spec vectors and the comparable vector that we build. This is also a work in progress, and we're advancing now. Finally, what we said is that E-graphs actually find equivalences. We can tweak that idea into find optimizations, not through a cost function, but by enlarging the equivalence class. And the idea that we had is that if we can model designs through terms, we can also model attacks through terms. And if we connect properly those 2 E-graphs, maybe we can have some sort of evolutionary loop between the 2. We can have an E-graph that designs hashes and E-graph that attacks those hashes. At the time being, those 2 systems actually exchange scalars. They do not read each other's designs fully, but that's going to be a work of the future. We've been working in the reaction of the blue team, actually acknowledging the attack and keeping track of the families of designs that have been already beaten. At this point, it's we have to know that this is not actually performing any attack. This is just modeling families of attacks. And it's ranking those families of attacks in terms of time consumption or complexity. So this is still a work in progress. What we have in the future is tweaking some of these very small parts. For instance, benchmarking, taking account some reference implementations, and pipelining and connecting all the expressible designs, write a polished CLI, the documentation, and also expanding the interaction between the 2 E-graphs for more complete information. That is, we want the e-graphs to be able to read the design instead of a summary of the design. So that's pretty much it. We have been very recent with this, and we're very happy with our progress. If you have questions, comments, just reach out in the Telegram group, and we'll get in touch. Thank you.
Thank you very much. And then if anyone has a question, there's a bit of time in the changeover, and the next talk otherwise is going to be about, I guess, GPU related things, and Sue1 is going to tell us about lowering lean and stable HLO and the bridge between both.
Yeah, so the lean stable HLO is kind of like a compilation step for the from the lean to stable HLO, which is the made by Google, like for the parallelized execution layer for the LLVM. So it's kind of like a MLIR step for the language. So it is kind of like writing the cryptographic protocols in Lean, and we can just do some formalizing this protocol, and then we can do some compilation over this Lean DSL, and we can get some Zmod P under the Zmod P for the cryptographic protocol, and then we can serialize this protocol to the stable HLO MLIR text. So this point is we should trust this serializer for the writing the exact text, because it's kind of like inspired by some CompCert C compiler and also for fiat crypto style. So it is making some one untrusted point for this making cryptographic protocol in the stable HLO. So and then we can do some like compilation from the stable HLO to LLVM or the bytecode thing, and then if we connect them with the formally verified thing in that layers, then we can do all over the formally verified execution for the cryptographic protocol. Yeah. So I made the like KZZ commitment scheme in Lean, and then we can execute on this on GPU. Yeah. Thank you.
Nice. Very, very cool. Any questions?
Yes, I have verified implementations of the BN curves and also connected to the prime IR. So I have a compiler for that.
Yeah, there's one point is like EC thing is not really like verified, because like it is from the like fiat crypto is written in Coq, and then I just ported like for that thing to the Lean, but it's not really like 100% like formally verified. So
yeah,
maybe it's like visual.
I have a port between them which I can share.
Oh,
yeah.
Thank you.
So, but great work. That would be nice to connect.
Yeah, thank you.
So there's a lot of activity on the compiler side, I think, at the moment. And so the next talk is also about compilers and also about MLIR, which is Tobias, who's going to tell us about basically putting an MLIR into Lean. You muted, Tobias.
All right, so we have a project called VEA. It's a verified MLIR style compiler data structures that we are developing since a while, with like also support from Ethereum. So the key idea is that verified compilers is a well-established thing. So they're perfectly well proven. They are sometimes painful to develop, and one of the biggest concerns is that they have been typically quite disjoint from the production compiler communities. And MLIR is a tool that pretty much is used across classical compilers, maybe even to model SMT solvers. LVM is used in Lean as a backend. There's a lot of AI and scientific computing that's based on LVM or MLIR, and even like hardware design tools like Circuit are based on MLIR. So obviously, in theory, you want to maximize this reuse, and so MLIR in theory is a tool that enables that reuse. So it breaks down the like all the different users of compilers and pretty much exposes the individual abstractions as so-called dialects that makes it easy to kind of transition from a classical compiler to an EDA tool to a crypto tool, all these kind of things. What makes MLIR special is actually not so much that it's a compiler, but it's a data structure, right? So if you look at the left here, LLVM and MLIR both use the same kind of data structure, which is a data structure to model static single assignment form code. And that means that whenever you have a sequence of operations, rather than a purely functional representation, it's actually very easy to jump from a definition A to its first use, the second use, the third use, or from any use to the definition in constant time. And the way that is done is that MLIR uses a relatively pointer-heavy data structure to, for example, to jump from a definition to the first use, to the next use, to the next use, pretty much random access on that data structure. So if you think about how to verify data structures in Lean, to model this in Lean, you pretty much need to verify a double linked list in 7 dimensions. So the way we do that is Lean obviously doesn't have pointers, but you can just see a pointer as a natural number. You can simulate a heap by using a hash map that maps pointers to the objects, in this case operations. And the operations themselves, again, refer to pointers, just, again, using these natural numbers. That means we can directly, like one-to-one mirror whatever MLIR does in its C++-based implementation in Lean, at the cost of a relatively complicated data structure with a lot of hash map interactions. We have, independently of this talk, we have an optimization that gets rid of the hash map and makes it actually perform fast. But conceptually, it's just like a pointer-heavy data structure that must be validated. The benefit of this is that we get the asymptotics right. So any kind of algorithm that you implement over MLIR, where you iterate over the operations, over the blocks, where you start rewriting and translating, MLIR is optimized for asymptotics. So you get constant time or logarithmic time or like time in the number of users, complexity for pretty much all of the operations that matter when you interact with a compiler IR. We also tried our implementation. Here we call it chainmail. Compared it against MLIR, and what you see is that on a synthetic benchmark with like 300,000 operations, we are only 2x slower than MLIR. In this particular case, the benchmark is likely not bottlenecked on the data structure, but mostly compares like Lean versus C++ code. On dedicated data structure benchmarks, we are roughly 5 to 10x slower if we go through the hash map. If we go through our optimized data structure where we eliminate the hash map, we believe we are pretty much matching MLI even constant time. So constant time optimization is not fully yet implemented and not fully proven. But the nice thing about the hash map based data structure, that's already fully proven. Now, how do the proofs look like? So we have 3 levels of proofs. One is memory safety. That pretty much just means that any pointer that ever appears in the data structure exists in our hash map. So we don't have any pointers that don't exist. Then we have data structure well-formedness. That pretty much means that a double linked list, or all these different double linked lists in the MLIR data structure, are consistent. So a pointer going to the next element, and then from the next element back to the previous one should show a point to the very same operation. And then we have an entire layer of functional correctness. Particularly, we have...
Perdona, vosaltres teniu tableros de MDF de un centímetre.
I think there's...
sorry.
Exactly. So for functional correctness, we have an entire layer of functional correctness. So we have an interpreter for LVM-IR, RISC-V, and a couple of other LVM and MLIR dialects. And what was probably the most challenging proof to write, we have a proof that if you have a local rewrite and you prove it locally correct, we can lift that to the formal correctness proof of the full program. Meaning any local proof applied at any location in your program will preserve global program semantics. We use that to build an LVM to RISC-V backend, going from LVM to RISC-V, connected with the sale extraction of the RISC-V spec, also supported by Ethereum. Here in the middle, proofs are validated using Lean's BV-Decide. And yeah, we have a couple of dialects already. We have a couple of transformations. And it's a relatively active project. So we roughly get 5 commits per day, have 17 contributors. We are close a median PR. Close time is 8 hours, and yeah, so please try it out. let us know. It's still a very early prototype, but we are interested in feedback. We are hiring if anyone wants to work with us. And the last thing before I advertise an event, I want to very quickly show you what it actually can do, because I think it's quite nice. This is a fast fast NTT. So pretty much you just have a large MLIR file. It's a textual representation. This is the test file. So this is the expected output. This is the MLIR input. And so VEA has a tool called VEA-OPT, where you can run a number of passes to translate from LVM to RISC-V, and you just run it on the file. And it behaves like MLIR, like a normal compiler. Like you take a textual representation of its IR, you turn it into the data structure, you run passes on it, and you print it back out. And all of that works. This one is not completely sorry-free, but we expect that to actually soon be completely sorry-free. And yeah, then we can build more of the compiler. I want to close with a short advertisement. So in September, we have a small event on like verifying LVM MLIR in Lean. It's in Cambridge, beginning of September. It's very small, so I'm not sure how many spots we have, but if any of you is interested, just drop me an email and I'm sure we can find something. Thank you so much, and let me know if there are any questions.
Thank you. And yeah, I've done some VEA code in LLCK, so I can confirm it's pretty sick. All right, so I think that's the end of the compiler, at least the kind of main compiler section before we get to the smart contract compilers. And so now we can switch to, I guess, the last topic of today, which is the EVM and then smart contracts. And we'll start with the Monad guest program verification effort that Monad have been doing.
Hi everyone. Thanks for the invite, Alex. Today I'm going to talk a little bit about the work that we're doing at Category Labs to apply formal verification to the Monad execution clients, and in particular the guest program that we are extracting from it and sort of working towards like Ethproofs compatibility and producing a compatible guest program. A blockchain execution client is obviously a really sensitive bit of software. There are lots of ways that you can get this wrong with pretty bad consequences. And so we have, for the last 18 months or so, been going pretty hard on applying formal verification to the actual C++ that we're writing in Category Labs in the Monad client. Pre-2026, this was slow going. It was hard to make progress. Verifying such a large piece of software is tricky. It's a huge volume of proof to produce, a lot of code to reason about, lots of sort of invariants, lots of things that you need to keep in scope. And so we were making progress, but it was slow going. This year we have been able to sort of really accelerate what we are doing by way of like an agentic proof workflow, which I will go into in a second. Our approach uses this tool called Brick from a company called Skylabs. It takes the real C++ in the execution client, embeds it into an AST in Rock, and provides you this tool called Iris, which is a set of separation logic rules for reasoning about the actual sort of standardized C++ semantics. Our aim is to produce like fully machine-checked proofs of correctness for the whole execution client, top to bottom. So we've been able to make much faster progress by using this like agentic workflow, going back and forth with Codex and Claude to help us figure out how to prove correctness for components of the client. Generally speaking, our workflow is to go back and forth, stating sort of specifications for correctness, refining them, and then asking the agents to produce concrete counterexamples. We found in practice that they are generally pretty good at finding counterexamples, and you can make a lot of progress towards good specifications by having them sort of attack your specifications with counterexamples. And at the point where they slow down and stop making progress, giving you counterexamples in ways in which your specs are broken, at that point you can switch over and begin to have them actually produce proofs. Generally speaking, they're good at helping with the sort of the creative parts of working with Ethereum provers, things like loop and concurrency invariance that the underlying like proof automation tool sets in Brick can't automatically derive. And so far we've cut like 4-person week times for proving particular specifications down to like less than a week of effort for one engineer. And we're internally doing a lot of work to sort of make this accessible to regular engineers and to bridge the gap between the people who are writing C++ and the actual formal verification engineers who are doing it. We've had some, as a few people have highlighted in their talks, we have a like certificate of this being useful. We are working internally on a feature for the Monad network. This is not like an Ethereum feature. This is a new feature for Monad where we have a novel commitment scheme for a different abstraction on storage. And so we've been working pretty hard on formalizing this top to bottom. We have a C++ implementation of a new commitment function based on Blake 3. There were pen and paper proofs of correctness, and we ported these over to Rock and produced proof that this new commitment scheme can't produce collisions without the underlying Blake 3 compression function also colliding. The use of the C++ embedding into Rock also gave us a useful certificate here in that it found a really subtle bit of undefined behavior in the implementation that none of the sort of standard compiler tools were able to find for us. ASAN doesn't flag it, compiler warnings didn't catch it. Nothing else identified this, and even prompted to hunt for undefined behavior. Regular like code review with frontier models didn't find the bug, and we were able to sort of minimize this and produce an example where we could demonstrate that GCC actually did miscompile the program in the presence of this undefined behavior. And so we have an actual certificate of a safety and correctness improvement in the client that we found by using this sort of iterate and prove loop with agentic workflows. I'll show in the chat after this. We have a blog post out today that goes into a lot more depth on all of the stuff that we're doing, as well as some of the other places where we've successfully verified parts of the client. And to sort of conclude, this is all in service of producing a more correct, safer client, and that carries over to the work that we're doing, producing a RISC-V compiled guest program for Ethproofs. If you don't know that your client compiles correctly, if it has undefined behavior or behaves incorrectly, then your all bets are off with your guest program. And so this is all in service of producing a safer guest based on the Monad execution client. Cool. Again, thank you for the invite. Happy to answer any questions quickly in the changeover time.
Thank you very much. We have one message in chat, but it's not a question. Okay, and then so then we'll have I guess 2 other talks on guest programs of some kind. First EVM-SM and then EVM-Cell, which are both very new projects. I'll let Yoichi talk about EVM-SM.
EVM-SM is an EVM guest written in an assembly and the RISC-V assembly. And the idea is that, okay, well, at the end we are trying to make ZK EVM, and we have like RISC-V ZK VMs. So we need some program to run on top of ZK VMs, and we want theorems about correctness of this RISC-V bytecode. And what's the simplest way to do it? Or maybe the simplest way is to write the assembly and write theorems about it. And there are like program logic for assemblies from decades ago, so we can maybe just use it. And it turns out LLMs are really, really good at it. When I keep agents, one agent in a loop, it produces roughly like 10 theorems per hour or something, and that covers like 4 or 5 basic blocks, and that kind of looks practical enough. So I've been running this, and actually Derek has been running this too. And then, so we have been producing theorems about RISC-V assembly. And one of these is like the heaviest piece is the correct division algorithm for like 256 bits divided by 256 bits, and it's proven the division, and its performance is okay. And also the Lean theorem also tells you the worst case number of steps, instruction steps, and for division it's 954. 4. And then like when you run it, like the performance is sometimes very good, like compared with the other two. Sometimes very bad, but no, not very bad, but I mean sometimes worse. And then like especially when you divide by small number, it's worse. But the nice thing is like anybody can file a pull request saying like here's a faster algorithm, especially for like divide by big numbers, and here's a theorem, and the theorem is not broken, so it's guaranteed to division, and it's very easy to review. And I can maybe merge it very quickly. There are some other efforts going on, like not all opcodes are done. Like there are some like exponentials and signed divisions. Basically, these things are in progress because like these had to wait until the components are finished. Like the exponential use multiplication, and SDiv uses the usual division or its subroutines. So like they were kind of waiting until these components are done. The comparison against the say RISC-V spec is still in progress. I mean, I guess this is becoming painful. Like every time I say formally verified, I have to like put an asterisk around it. So like this is becoming more of a priority right now. We have been running the test conformance, and this there are still errors, but these are mainly about gas accounting, and we have confidence that this approach works in the sense that there are like enough amount of memory to do all the calculations. We still need a specification in Lean about the stateless execution client, and not just for smart contract verification, but also about like parsing the block, parsing transaction, parsing receipts, and so on. And in a call like this, when I say this, like somebody might remember and come up with one. So that's why I'm saying this. Thank you very much.
Thank you. Any questions about this? And otherwise, we have a fairly related talk, which is EVM Cell, which Francesco can tell us all about.
Hey guys. So I'm Francesco. I'm part of the ZK EVM team at the Ethereum Foundation. I kind of stumbled across the effort the EVM ASM effort, and it became particularly interesting to me because I've been primarily focused on integrating ZK EVMs into consensus clients, and I was just particularly interested in how we can kind of harden the security argument around it. So explored EVM ASM, and then essentially stumbled across Sail, and kind of set about essentially defining the EVM in Sail. So for those that don't know, I'm sure many of you do, but Sail is essentially a language that is purpose-built for defining ISAs and the semantics of instructions. So we've essentially got an initial implementation. The way that we've structured EVM ASM, we've essentially defined kind of the core opcodes, the semantics, similarly for gas and call frames, and then all effects go through this kernel interface. So we have a kernel interface for accessing state, making modifications to memory, making modifications to transient storage, etc. So it's pretty kind of explicit in that regard. And what's nice about the Sail implementation is it has pretty rich tooling. So you can extract it to various different backends that allow you to do various different things. I must say that this is still very new, so much of this I have not done personally, but I believe RISC-V has been defined in Sail, and many of these kind of flows have been evaluated for that. So the assumption is that it should work similarly. So kind of the next step would be to extract the EVM cell specification into Lean, and then potentially try and support the EVM ASM effort in terms of being a specification to test it against. And more generally, for any kind of RISC-V guest, we can evaluate compliance. There's also Islaris. I'm not sure if I pronounced that correctly, but it allows for symbolic execution. So this is quite interesting because we can potentially automatically generate test vectors. So if we introduce new EIPs or new features, the hypothesis is that we should be able to automatically generate test vectors for the new feature, and then use those test vectors to to evaluate various clients. And additionally, it could potentially be extended to for use in contract verification. I have compiled this down to C. We have 100% of the East test, both the state test and the blockchain tests, working well. What they're passing essentially. We also are able to compile this down to RISC-V. So I've compiled this down to RISC-V and simulate or emulated it on Spike, the Spike emulator. And I believe you can also extract to ROC as well. Yeah, I guess it makes sense to just note that the memory and kind of state interfaces are currently defined as kind of abstract using C header files, which are then subsequently kind of satisfied in the target environment. Similarly for the cryptographic operations as well. This is a moving, it's under rapid development. So the current commit in EVM sale is pretty old, and I'm hoping to commit the 100% test compliant version within the next day or so. So yeah, that's all from me.
Yeah, thank you. Yeah, so there's a note in chat about setting up, I guess, a call with the sale people to talk about. So Tobias is obviously involved with sale in Cambridge, but I guess we'll keep things moving to try to not run too over time. And so the next talk will be about the verified Viper compiler. I think I'll share the slides in this case. And Ramana's going to talk to us about what I think is the most complete compiler verification effort for smart contracts. So let me share quickly.
Thanks, Alex, for the introduction. Hello, everyone. I'm Ramana. I'm speaking on behalf of many different organizations. Viper, which many of you will know, is one of Ethereum's smart contract programming languages. Ethereum, which is the project that I started to do formal EVM semantics and smart contract verification, and Sequent, which I co-founded, which is doing formal verification for everything, and we're in particular doing smart contracts at the moment. This talk is about the verified Viper compiler effort, but as anyone who thinks for a second about what compiler verification means, that includes formal semantics for the target and source languages. So I'll start, since we just heard from two speakers about EVM semantics, I'll start with the bottom end of the compiler, which is on the left here. The Ethereum EVM semantics is, I would say, a production quality executable formal semantics in the whole for Ethereum prover. We had it for Prague, and it's recently been upgraded to Osaka, and it's going to be upgraded for Amsterdam as soon as that hits mainnet. Yeah, this is validated in multiple ways. So if this EVM sale that we just heard about, doesn't export to whole 4, we could think about doing a proof for an additional bit of validation, but that doesn't exist yet. So what we have for validation is the East test suite with about 99% correctness on that. And the reason it's not 100% is just because I haven't done like a fast execution mode for it yet. I'm doing execution in logic, and so some of them time out. I can run them for longer, and then we'll hopefully get the 100%. But beyond just executing the semantics, we can also prove things about the semantics. So we have validation of the semantics both on passing the tests, but also proving properties about it. So for the EVM semantics, we proved things like gas monotonicity, and that a call fits inside of state frame. So when you make a call, you only touch the storage of all the contracts that got called during that call, but not anything else. So the rest of the machine stays safe. And this is useful, obviously, for proving things if you want to do smart contract verification at the level of bytecode. So in addition to the EVM semantics, because we're doing compiler verification, we also have done the formal semantics for Viper, the programming language. And for that, we have validation for the semantics just in terms of the Viper test suite. So the Viper language has its own test suite for its language, and we check We don't have full coverage of their test suite at the moment, but that's ongoing work. But we have a pretty comprehensive feature coverage, so we cover the entire Viper language. So this compiler verification project, I'll speak a bit about the rest of the details in a second, but it's currently kind of paused because Sequence is working. It's kind of paused pending funding. Like if we get funding or contributors to kind of finish the rest of the compiler verification, we'll go ahead and do that. But we are pursuing opportunities to do smart contract verification and outside of Ethereum formal verification for the time. We have limited bandwidth, so that's why this is in the state that it is at the moment. But it'd be great to finish it. Part of that, it builds on top of the Viper semantics. We have a program logic for Viper. It's like a whole logic that lets us do smart contract verification, and we're doing that with our agentic prover agent that can automatically prove correctness of many smart contracts. So when it comes to the compiler correctness stack and the compiler correctness proofs, we had a big effort on this in the beginning of the year to get a definition of the Viper compiler, which is also like a production grade compiler. It's modeled on LLVM, or it uses many of the same concepts as LLVM, and it does many optimizations. We did the definition of the compiler and proofs and the proof framework, proof infrastructure framework for many of the optimization parsers and compiler parsers. Those operate on the Venom intermediate language, which is Viper's main kind of intermediate language for its compilation. So those are about a half done, I would say. Like we've got about 10 of the parsers proofs completely, and then partial proofs for many of the other compiler parsers. We've also taken a stab at the other 2 bits there, which is going from the Viper source code into this intermediate language, so the lowering phase, and the final bit of Venom to EVM bytecode. Those are kind of scaffolded, but the proofs are still open. So that's the current status of the verified Viper compiler. As Alex said, it's a big project. There's many, many lines of code in here. A lot of them are AI generated, of course, and a lot of them are with our prover agent, not just using a bare LLM, but we've got an agent to do the proofs for us. I'm happy to take questions on that.
Thank you very much. I'll just see if there's any questions. This is, I think, very, very cool work. And then I guess, have you played around with trying to port contracts? Yeah.
Oh, trying to port contracts like Solidity to Viper?
Or any, I guess Solidity is the main one, but yeah, any other language.
We haven't done like a serious go at it, but we've thought about it, and it's obviously as soon as someone comes to us and says like we definitely want you to do it, we'll do it. And I think I just remembered also that Yoichi said that he wanted a formal semantics for the full EVM, including the blocks and the transactions and like the full state machine. And that we have that here, like Ethereum models all of that. So if you want an EVM a formal EVM semantics to look at, I suggest taking a look.
Well, do you want to upstream your semantics to Cell? Because you could then extract from Cell to whole 4 and validate them. Or like at least validate that the upstreaming to Cell is consistent.
I think the way that I would rather do it than upstreaming is to import the EVM sale semantics and then do a proof of equivalence, because then we get to keep the semantics in the format that I've defined it, which is suitable for doing all of our meta theory proofs and doing the compiler correctness proofs. I think it's like there's different ways of formulating these things.
I say you upstream very loosely here. Like you would keep the whole 4 ones, just validate whatever is in Cell against the whole 4 ones.
Yeah, it would be really nice to get a proof of correctness there, proof of equivalence.
So one motivation is if we do move towards having fewer guests, then having spec diversity and cross-checking the specs will become more important.
Exactly. Yeah, spec validation is very hard.
Yeah. Okay, and then next up is Verity, which is a recent effort as well to have smart contracts.
Real quick, could I ask a question before we proceed? I don't know.
Of course, yes.
Do the raise hand in Zoom. I wanted to ask, for the purposes of formalizing Viper and etc., how do you think about gas introspection, and like how do you connect like the high level spec to like the low level?
That's EVM? A good point. Yeah, so Viper does not have gas. Like you kind of assume that your contract gets as much gas as it needs in the Viper semantics. So it's not modeled there, but you do have the low-level opcodes, like you can ask for you can do tricks in the EVM or ways to kind of introspect on the gas. Part of the compiler proof is probably going to be the hardest part, and it's the bit that we haven't finished it yet, but we have a plan for how to do it, which will involve adding a gas oracle to the Viper semantics that lets us say how much gas you started with and how much you actually used at any point. And we don't calculate that. We just take it in as an oracular input at the start of the semantics. And we know that such numbers exist for every time gas is introspected because there's a real underlying machine at the bottom. So there's a kind of informal sketch of how I would do that proof, but it remains to be seen whether it gets done formally. If that makes sense. I hope to talk about it offline as well.
Yeah. So gas is a nightmare.
Thanks.
Gas is a nightmare, I think, is the TLDR. Okay, and then yes, the next talk is fairly related, which is this time in Verity. Verity is, I guess, a different attempt at verification, which is having a lean DSL to which you can port things, and then there's some compiler verification effort that's also on the way. Do you want to let me know if you want me to share the slides or if you're sharing?
I'll share if that's okay.
Yep, go ahead.
Yep. Can you see it?
Yep.
Okay, perfect. So hello everyone. So I'm Ben from Verity, and I didn't know really how familiar you guys were with formal verification and so on, but considering all of the talks I listened to today, you guys are pretty familiar with formal verification from what I understood. So I'll pass the beginning of the presentation just to present Verity. As Alex said, Verity is a lean DSL to write smart contracts. And the main goal for us at Verity is to be able to model Solidity smart contracts, even though we do compile to Yule and then to Solc, to EVM bytecode, my bad. The goal for us is to model your Solidity smart contract in Verity and then be able to formally verify it directly in Lean. So 3-step process. First, you model your smart contract in Verity. Second, you write the specs, the theorems, the invariants. You can call it whatever you want. And then you send an LLM to write the proof. So in general, in the classic formal verification space, we had before LLM were so good. So basically before in 2025, basically, well, we had SMT provers do the prove it part, where basically they're going to try a lot of possibilities, and sometimes they time out. And the problem was on non-linear code, which is a lot of code when it comes to DeFi, well, they time out, or we take as an assumption all the mathematics in the protocol, this kind of stuff. So here, the big change with using Verity and other formal verification tools that use more reasoning and LLMs to write the proofs is that you're able to do unbounded formal verification and you're not using raw compute, you're using an LLM that is actually able to reason on the code and to prove that it's correct using mathematical arguments. So we do that. We model, spec, and prove code. So to give a small example of what we've done, so we worked a bit with Lido v3, and yes, very, very simple function. For example, this function, we model it in Lean, in Verity, and sometimes we do have the features at the same level as Solidity, but the goal is it's been like 4 months for working in Verity. The goal is to have all of the features and to have feature parity with Solidity, and not really to reinvent a new language with original features and better features. Our goal is really to modelize Solidity, so we will have something very, very similar to Solidity. And once you've done that, you define the invariance. This is one of the invariants we defined for the Lido smart contract. In that case, is basically the fact that the vault is solvent, so you have more ETH behind every ST ETH, and when you do this spec, of course, you write it in Lean, and it looks like this in math, but you can also formalize it in English. All of that in the vision that in a future where everyone is vibe coding everything, you do not really want to actually audit code, but you want more to audit specs and to have a mathematical proof that the specs cover everything in the protocol, that the specs, the implementation matches the spec, and then you have to audit basically only the spec and not the implementation anymore, which is like probably way easier. Even though it's not that easy, but it's more easy than actually doing the whole implementation. And then what we do is that on the third step, what we do is that we send an LLM and we ask him to write a mathematical proof in Lean that the implementation, which is the modelization here, matches the spec, which is a bit like the theorem, the invariant, and to verify that the theorem, the LLM will do lake build, and if it fails, retrace, and like this you have an agentic loop. And if I actually have on my laptop right now four different protocols being proven, and it's been like 2 hours, and my laptop is in complete PLS mode because it's been 2 hours. Codex is running on the laptop to try to prove. Doesn't succeed for the moment, but I'm sure it will. So it's preferable to do that in the cloud. I had a cloud problem today, so weren't able to do so. But at the end, you have the theorem that is proven, and the theorem is basically on the example of Lido that ST-heat can only be minted if the vault's total locked heat exceeds its total minted ST-heat. So vault solvency in that case. And yeah, that's a bit what we do at Verity. If you guys want to prove software, want to prove your smart contract, well, you can send me a DM on Telegram, and if you just have questions, please do the same. Send me a DM on Telegram, and we can discuss it.
Thank you. And then we've got 2 more talks left. So the first of these 2 is going to be Leo, who's going to talk about his recent fun adventures in bytecode and AI and form verification in Lean.
Yeah, do you want to share it if you have the link?
Yeah, give me 1 second.
Thank you.
There we go.
Yeah, so this will be a short one, likely. It's a good segue to come after Verity. So EVM Smith is an experimental framework I've been playing with the idea of, the EVM ASM inspired idea of writing EVM bytecode directly, so not RISC-V, but smart contracts, and having AI write the bytecode directly and the Lean proofs at the same time. So combination of Lean and AI. And the first experiment that I did was actually to try to see if this actually makes any sense. So I'm using the Nethermind EVM Lean repo that has the Lean spec in Lean, EVM spec in Lean. And so I wanted to try to prove something complicated. So I had the AI write a small wrapped ETH contract, not the same as the standard one, doesn't have the transfer function, only deposits and withdrawals. But the property I was interested in was solvency. So basically, the contract has enough ETH to pay back all the people that have deposited money into it. And it's a pretty difficult thing to prove. It's an inductive property over any amount of transactions that you can have. But AI was actually successful at proving this. It took many hours with Opus 4.8, I think it was, or 4.7, not sure, one of these. But it was about, I guess, like 10 to 15 hours of thought. But I think this is pretty impressive, honestly. It's not the first thing that I tried immediately, but like definitely the most complicated one. And I think the fact that this was successful actually probably means that you could prove anything kind of reasonable, that you can actually argue about your contract, as long as it has that property, of course. The other thing I wanted to check is what if I take something that Viper has already compiled? Can the AI actually understand enough of the bytecode to make modifications and improve the equivalence of the 2 bytecode? So the idea here was to do like a custom storage layout thing where we don't want, for example, the Ketchak appended storage slots for mappings. We want to use something that doesn't run Ketchak. And this was actually pretty easy for Claude. It immediately was able to prove equivalence of the optimized version and the ones compiled by both Solidity and Viper. I think I had both. And after these, a lot of people were like, yeah, this looks great, but who's going to be reading these theorems? Like a handful of people can actually read these theorems and reason about what they actually mean in the context of EVM. So the next thing that I wanted to do is like, can we actually have a small EDSL inside Lean that kind of looks like Solidity, has some formality to it still, for some formalism, but lets us reason about it in a bit more high level. So then AI came up with a very simple DSL that was only enough for wrapped ETH because it didn't want to make it too generic at first. And I think it actually looks pretty nice. So like basically 100 lines of DSL code in Lean, and I think this looks pretty nice. There's a few more properties that look like this as well in a similar DSL. And there's a point that I think Yoichi was also making before, that like, do we even need compilers at this point? Of course, it's half what I'm saying now is half trolling, but yeah, it's pretty impressive what it can do in the context of writing the bytecode and writing the proofs immediately. And if we can have high level specs like these properties that kind of look like the high level code anyway, and people would be reading these only and not having to read the whole bytecode, I think it is a possible future. So yeah, so there's blog posts about each of these items in the first link. The framework itself is in the second link. So yeah, thank you.
Can I just clarify something? What is there an EVM semantics in this work, or is it kind of like you figure out what the instructions mean as you need to?
Yeah, it uses Nethermind's semantics, the EVM Lean repo.
Oh, okay.
I'll put a link to the EVM Mule stuff in the chat.
Did you make some comparison about the cost of the proofs comparing to other methods, just with LLMs? I mean.
No, not really. I only tried with Claude. I saw that you guys did this comparison recently.
I mean, yeah, we made a comparison on the models, but not really on the method. The method was always using Verity and not directly the bytecode. And that's why I'm surprised that, like, I think it could be very expensive using directly the bytecode. It should be like very hard for the proof to actually pass comparing to Verity. That's why I'm asking.
From these experiments, it looked fine. Anything that was like the solvency property with reentrancy and everything also took a long time because the EVM Lean repo wasn't like super fitted for this. So it had a lot of Yule stuff, but not a lot of EVM scaffolding. So part of these like 10 to 15 hours that I mentioned were actually writing all this scaffolding to be able to reason about EVM directly. So it's hard to say exactly what was the scaffolding, what was the property proving. But when I tried smaller things like the manipulating the EVM bytecode directly to write this custom storage layout and then proving it, it was immediate, I don't know, a matter of seconds or minutes.
Okay.
But I would expect the solvency to still be hard, even if we had the scaffolding already. But I can't tell you exactly how long it took just for that.
Okay. And that was Opus 4.8. Sorry.
It might have been 4.7 because this was, I can't remember exactly when 4.8 came out. And the first one was like end of April, beginning of May-ish. So it might have been 4.7, but could also have been 4.8, but definitely not Fable.
Okay, thanks.
Okay, and then we've got the last talk of the day, which is by Anya from Augur. And this is, I guess, a bit different, which is just looking at incentive security.
Yeah.
Off to you.
Thanks. So yes, I'll be telling you a little bit what I've been doing at Argo. And like Alex said, I was talking about incentive security that we formally prove with ACT. So I'm kind of hoping that most of you have heard of ACT before, but just in case you haven't, when I say act, I mean this pipeline here. It's like a specification language in which you can describe a behavior of your smart contract, derived from the source language probably. And then what we do is prove it equivalent to the actual EVM bytecode using the HEVM symbolic execution engine and its equivalence checker. So this is also maintained by Argo. And then the real reason why you do it, because then we extract sort of a state transition system, a high-level way to reason about the smart contract. We extract it to Rock and Lean. And then in that, you can then, in Lean, for instance, define and prove properties like solvency. So we did solvency for AMM. But I want to talk to you about what we are currently doing. So this is the work in progress part. We are not interested just about code security, but also economic incentive security. And we want to formally prove it. So we use the already existing ACT spec for your smart contract. And then we automatically generate a model to a tool that is called Checkmate, which is designed to prove incentive security. So what do I mean by incentive security? It's that the users or players are incentivized to follow the honest protocol, right? And incentivized, it means there is some monetary reward for when you're behaving according to the specified protocol. But additionally, you also want to make sure that the honest players cannot be harmed, no matter how other people or agents behave, and that the protocol itself is collusion resilient, which means hush, hush, don't tell anyone what we're doing doesn't pay off. You will always be worse off in the end if you're doing something that is not according to the protocol. And these three properties, they have like a mathematical formulation that the Checkmate tool automatically checks using the SMT solvers. So what we're doing is going from the ACT spec to Checkmate in an automated way. And I just want to give you the high-level idea of how we're doing it. So the idea is that the players are the addresses of your smart contract, and then the actions they can take are the transitions, so public functions of your Solidity contract, say, right? And we then set the caller to be the player we're interested in, so the specific address we fix. And then what their payoff is in the end, the economic incentives, can be defined from the state variables that are available to you, balances, or other storage variables in the contract. And the trick is that this final model, this game tree that we produce, respects the call graph of the smart contract. And additionally, all of the preconditions of the transitions, think like require statements in your code. So obviously I'm hiding a lot of detail in this picture here, but I just wanted to give you like the idea of what you can do automatically from a smart contract to the economic incentive. One other line of work that we're also doing is replacing this equivalence check that is done in HEVM from something that you can prove directly in Lean. So we will call it, I think, EquiVM. It's not open source yet, but it will be soon in a few months. So the idea is exactly to do the bytecode equivalence with spec and some semantics of the EVM bytecode, and you can then run agents to check for equivalence. So I didn't want to spend too much of your time. So I will stop here and you can ask me questions if you like.
Yeah, thank you very much. And so I think if you're looking at Lean as well, you might have seen there's an econ lib that started in Lean recently, which would probably be a great place to formalize whatever AMMs and other incentives and economic mechanisms that are implemented in smart contracts. And then you could tie these all to specs.
Mm-hmm.
Okay, so I think that concludes all of our talks. I think as usual, the Ethproofs call has run off by about 30 minutes, which is right on time. But that's basically it for today. If there are no other questions, obviously I'll invite every speaker to put their slides in the chat and see you on August 14th to, I guess, talk about binary fields again. Maybe there'll be an executable specification for Flock in our clip, maybe with a compiler. Who knows? We'll find out in a bit over a month. And maybe proximity gaps will be solved as well by then, hopefully. So yeah, thanks everyone. I don't know if you have any final comments, Justin, and advice to you all in August?
No, I just wanted to thank you, Alex, for hosting this call. This was great. And thanks, everyone. See you very soon. Bye, guys.
Bye, everyone.
Bye.
Cheers.
Bye.